This video will be about mass spectrometry. So we are going to talk about a mass spectrometer. Mass spectrometer is a particularly useful tool in chemical analysis, and we happen to have exactly the right resources for approaching this thing. The point of a mass spectrometer is to determine the masses of charged particles. Now, in a chemistry setting, in an organic chem setting, we use a mass spectrometer to determine the mass of parts of a molecule. We break the molecule into pieces, determine the mass of parts of the molecule, and then kind of compile them back together to determine what the overall molecule was. I'll get into that in the second half of this video. I'm going to do the first half just talking in a physics sense about the mass spectrometer, and then in the second half I will swing around and do an example of using this in an organic chem setting. And I will make sure in the middle of this thing to provide you with a spot where I say this is the end of the physics part of this and kind of the end of what you need for this course, and leave it at a from here forward, this is an application that you might use, especially in organic chem, though it may be helpful to see it worked out for this course also. Alright, a mass spectrometer works like this. We are going to have particles, charged particles, that are moving this way. We would like to find out what they do and what they are, so we're going to bring those into a chamber that looks something like this. As these particles enter the chamber, they are moving at a constant velocity because there's nothing to mess with them. But then we would like to bring these into a region where there is a uniform magnetic field. When the particle first enters this region, we're entering horizontally. And because of this magnetic field, we are going to feel a force that points downward. If you're not completely convinced, take a moment and right-hand rule this and you'll see it. So now our particle bends, well, the path of our particle bends, and now it's moving this way. But at that location, it's going to get a new force that points inward this way. We have seen this kind of a thing before, and what we know is if we keep getting this perpendicular force, we are going to eventually hit the wall. So we make this mass spectrometer with a wall here that is a detector. And the only thing the detector has to do is tell me where this thing strikes, where the particle strikes. From there I can get some information. I'm going to erase a couple of things off of this picture because the picture gets really busy really fast, and I'll zoom in. So I've got this, and let's get rid of some of these other pieces. You can trust that the magnetic field continues even out where that dot isn't. And this detector is going to give me this distance. This distance happens to be the diameter of my circle, so from that diameter I can get a radius. Now I've got some good information to work with. So I would like to do this. I'd like to say the force on my particle is my magnetic force. The total force acting on my particle is my magnetic force. Now, yes, there is technically gravity also, but these charged particles tend to have masses like 10 to the negative 25th, 10 to the negative 26th kilograms, give or take. Multiply that by about 10 for gravity, and you're still looking at 10 to the minus 24th newtons, which is really small. comparatively, my magnetic forces are going to be, huge, right? Like, even if this force is 10 to the minus 24th, even if my magnetic force is only at 10 to the minus 10th newtons, that's 14 orders of magnitude higher. That gravitational force just doesn't factor in. It barely qualifies as noise. So I've got this kind of a thing. My magnetic force is my total force, which is QVB. Now it's QVB. I'm not going to worry about the perpendicular part because I'm going to make sure that if my path of motion is in the plane of the screen, that my magnetic field is perpendicular to it. So V and B are already going to be perpendicular. My total force, as I know, is mass times acceleration. My acceleration, because I'm moving in a circle, is going to be centripetal acceleration. So I'm going to get a V squared over R. Now I can put some pieces together. If QVB equals M times V squared over R, I can cancel a V, and I'm looking for my mass. So solving for my mass, I get QBR over V. Now I can do something with this. This is enough because Q is a known quantity. When I do mass spectrometry, I know the charge of my ion. I generally singly ionize these, so most of the time, actually pretty much all the time, my charge is going to be plus E, so plus 1.6 times 10 to the minus 19th coulombs. So that's good. My magnetic field. We haven't talked about this in this course yet, but magnetic field is something that we can control very precisely. So my magnetic field comes down to turning a dial. Radius, that's a measured quantity, or the diameter is a measured quantity, and I can divide by 2. And so velocity is the thing that's left. The last thing we did before this was look at a velocity selector. So what we are going to do is have this thing go through a velocity selector first. And now I know the speed of my charged particles precisely, which means I know V. So I get this equation that is very direct, and that just tells me here is the mass of my charged particle. Now I'm going to go through and do this in the context of organic chem. So now we are on to the organic chem part of this. With organic chem, most of the time we are trying to figure out a identity of a molecule, but we don't really get what that molecule is ahead of time, otherwise we wouldn't be figuring anything out. I'm going to try and do this with the idea that we already have the molecule in place, but we'll see how that goes. So let's say I'm looking at a molecule like this. So this would be the CH3, C double bond O, CH, C, CH3, CH3, and I'm going to do some quick math. Carbon has a mass of 12 AMU, where 1 AMU is the mass of a proton, so equals 1.67 times 10 to the minus 27th kilograms. Carbon has a mass of 12 AMU, hydrogen has a mass of 1 AMU, and oxygen has a mass of 16 AMU. Those are numbers I just get off the periodic table. Number of carbons, I've got 1, 2, 3, 4, 5, 6. Number of hydrogens, I've got 3, 4, and 3 more is 7, and 3 more is 10. And number of oxygens, I've just got the 1, so 16 AMU. If I add all these up, I get 98. AMU. That is my molecular mass. I'm going to look at what this is. My mass spectrometer is going to give me some values. It's going to give me a couple of readouts, and if I had kind of the technical specs of this thing, I might see the magnetic field and things like that, so I'm going to write those down. My magnetic field strength for this particular mass spectrometer is going to be 2 Tesla, which is not unusual for a modern magnetic field or a modern mass spectrometer. The speed of my particles, if I'm looking at something in the area of 100 AMU, I'm going to get something like 50,000 meters per second. These things move. And my charge, I know, is going to be plus E, so it's going to be positive 1.6 times 10 to the minus 19th coulombs. Maybe I do this whole thing, and I end up getting a readout of a diameter of my path of 4.33 centimeters. So I'm going to go into my equation. I said that Q V B equals M V squared over R. R is just D over 2. I can cancel a V, and I'm going to get that my mass is going to be D Q B over 2V. So then when I plug these numbers in, I get exactly that. Right, I get a number, but I'm generally trying to deal in AMUs, so I'm going to convert this thing. I'm going to say, so I'm going to get 83 AMU. What's going on is I have somehow or other a molecule that I have cut a piece off of, and what remains has a mass of 83 AMU. If I look, if I had 98 for my total, 98 AMU for my total, and I cut off and am left with 83 AMU, that means I've cut off 15 AMU. 15 AMU is a carbon and 3 hydrogens, so I could have cut off here, or here, or here. Any one of those would have left me with a mass of 15 AMU here and 83 AMU here. In an organic chem sense, context, whatever you like, I would end up with a reading that looks like this. Organic chem does not require me, lab instruments do not require me to do the calculations every time, so I would end up with some kind of a readout that looks like this. Now I just found I had this big signal at 83 AMU. And then maybe I will always have this molecular ion, and that shows up, and that's a little smaller. The idea of that one I will actually come back to. So I get a signal there, I get one here. And then anytime I've got these signals, I'm always going to have a couple of signals nearby them that just come a lot of times from different isotopes. You know, maybe I've got a carbon-14 in there, or carbon-13 in there or something. So these signals are never quite as clean as individual lines. But maybe I've got something that looks like this. My highest signal, my highest number signal, is going to be my molecular ion. And this happens when I've got my whole molecule and I have stripped off an electron. Nothing else broke off, so this is going to give me my total mass. And all these numbers are going to be in AMU, so if I'm doing this from a physics standpoint, I'm going to have to do a little bit of converting. I found I've got this big signal at 83 AMU. It's like a big tall signal. And this scale over here is usually a relative intensity, which means that a high signal here is more prevalent. It's a more likely situation. So the most likely thing in here is that I cut off 15 AMU and I'm left with 83. The next most likely is that 98 minus 55 is 43. So the next most likely is that I cut off 43. This one I cut off 15 AMU. This one I cut off 43 AMU. Now in this case, again, I get to cheat a little bit just because, kind of quite a bit, because I know what my molecule is. But let's look at what that matches to. Cutting off 43 AMU would be, if I cut right here, this seems like a likely place to cut. I can cut off a CH3, that's pretty easy. This seems like a likely place to cut something. And let's see what that would be. I've got 2 carbons. I've got an oxygen. And then I've got 3 hydrogens. I get a total of 43. That is exactly what I'm cutting off. So this thing, this side of this, has a mass of 43 AMU. And then I'm left over here with 55 AMU, which is why I see this signal at 55 and this signal at 43. This is what I'm doing with these. I'm identifying, based on these signals, I can figure out what kinds of groups that I'm cutting off. Mass spectrometry on its own is probably not going to give me the whole picture. I might need some IR or UV vis or something else to go with it. But mass spectrometry is going to give me a reasonable idea of some of the chunks that I cut off. If I'm doing this in a chem situation, in a chem lab, then it's probably to verify a synthesis. I'm looking at the different molecules that I could have made given my reagents and using this to confirm which of those I actually made. In an unknown situation where maybe I'm, testing some kind of a vial from a crime scene or something, this on its own is probably not going to give me an answer. But once I start putting some different tests together, this can be a really good confirmation tactic. It's really, really powerful when you've got kind of the equivalent of a word bank, right? When you've got, I know it's one of these 5 things, I know it's one of these 30 things, 30 molecules, let me run this mass spec, and then you can look and see, oh yeah, this is consistent with this is consistent with that. You can identify quite a bit from that.